Okay. Excuse me. Welcome back. Excuse me. The attendance sheet is working its way around. Has everybody had a chance to at least download the PDF for problem set 1? Has everyone gotten access to the data? Has everyone logged into Piazza? Maybe? Okay. Please use Piazza to ask questions. They don't have to just be questions about administrative stuff, which is what they have been so far, but they can also be questions about the content. So if you have trouble understanding what a question on the problem set means, you can ask your colleagues, and someone may have figured it out. As a reminder, please don't give away answers on Piazza. Please guide your fellows in the right direction. Point them, go that way, but don't tell them exactly how to get there. So last time, we were just beginning to talk about how we describe the structure of networks. This first section of the course is really critical because almost everything we do later on about networks will depend on being able to think about a few basic concepts. The first of them is the degree of a vertex, which this is the degree right here. So this is degree of vertex I. AI in adjacency matrix notation is just the row sum. And we derive this very simple expression for the average degree, which we pointed out is just related to the number of edges and the number of nodes. Most things in network science are about counting. The difficulty is knowing what to count and some of the subtleties that go along with counting these things. So for instance, if you just look at the number of edges m in the network and divide it by the number of vertices, that doesn't actually give you the average degree because each edge touches 2 vertices. So it's twice the number of edges divided by the number of vertices. That gives you the average degree. And this, too, can end up being a very subtle thing. It'll appear in several other formula, and how we count things in terms of the endpoints will end up being very subtle. So keep in mind that, yes, most things in network science and this kind of statistics are about counting, but sometimes that counting can be very subtle. You have to know what it is you're counting, how big the set is, and where the things touch. Okay. So this is the average degree. We often talk about what we call the degree distribution, which is the probability that I see a degree of k. So probability that some vertex has k edges. And this is this is probability that a randomly chosen vertex chosen node has degree k, where we really mean uniformly at random. There are a lot of things in this class where we'll talk about stochastic processes or probability theory, and we're typically making an assumption about taking a uniform sample from some set. In this case, the set is the vertices. We're just going to choose one at random. What's the probability that that uniformly randomly chosen vertex has degree k? That's the degree distribution. There's a network. During the lecture notes at one point, but I guess I took it out. The probability distribution for the degree, it's defined on a support that goes over the positive integers. You can't have a negative degree. You could have a negative strength. So recall that the strength of a vertex is the sum of all the weights of its edges. So if the weights of edges can be negative values, then it's possible to have a negative strength. The sum of a bunch of negative numbers, for instance, could be negative itself. But in general, we're just talking about the degree distribution. This is defined on some interval that starts at 0 and goes to positive infinity. So the distribution might look something like this, for instance, in which this would be the average degree here, and this would be some notion of the variability of that distribution. I'll show you some pictures in a minute of some degree distributions, I think. So degrees are very important because they represent the connectivity of each vertex. So if I have some vertex like this, let A, its degree represents something about how it connects to the rest of the network. But this is a local measure of structure because I'm only talking about how A connects to the rest of the network. The average degree is something sort of a homogeneous assumption or homogeneous calculation about all vertices in the network, but the degree itself is just about the local vertex. Okay. Another property we think about is paths. And this has an implicit notion of distance in it. But don't be confused. We're not talking about Euclidean distance. There's no metric space here. And so instead we have to count things in order to construct some notion of distance. So a path in a network is some sequence of vertices, which you might denote sigma. Start at some vertex x. We then go to some y. We then continue until we get to some vertex. X connects to y, connects to some other things, which connect to z. So each consecutive pair of symbols here represents an edge. And that is what defines a path. A path has to be along a set of the edges that are in the graph. They represent a path that you could walk if you imagine yourself standing on a vertex and traversing across the edges. So you can think about bridges, for instance, edges being bridges and nodes being little islands. But the path represents the sequence that gets me from x to z. If the graph is directed, the path will be directed as well. And there's no guarantee that the path from x to z, that if the path from x to z exists, that the path from z to x exists as well. So it could be the case, for instance, that I have a bidirectional edge between x and y, but all the other edges in the path are unidirectional, in which case, if I get to z, I'm stuck. I can't get back to x. So if the graph is undirected, there's always a path back, because every edge is undirected. That represents a pair of bidirectional links, and so if you can get to z from x, you can get to x from z. Okay. So paths are important because they represent some notion of geometry, but it's not Euclidean in the common way that we think about it. So instead, we have to think about being able to count a sequence of edges in order to get somewhere. If we define the set of all z's that are reachable from x, that represents a component. So a component would be if there's some other set of vertices here, etc. This would be a component. All the vertices are reachable from x. If it's undirected, then it's strongly connected, meaning that for every pair of vertices in this group, they're pairwise reachable. You can get from one to the other and the other to the one. If the graph is directed, that's not guaranteed. It's possible that there's a set of vertices that are reachable from x, but x is not reachable from some of them. So that would be defined as a weakly connected component. A weakly connected component is a set of vertices that are not pairwise reachable, but they are at least one directionally reachable. Okay. So components essentially represent subgraphs of a larger network that are connected to each other by a sum path. And a lot of the techniques that we think about in this class will assume that you have a connected component. You're calculating the thing on something for which there are pairwise reachable paths. Some of the calculations we do will generalize beyond that, but at least at first we're probably going to be focusing on strongly connected components. Okay. This notion of distance that we are thinking about here, if I have some, how do I extract that from the graph? This is where we start using algorithms to do these things. It's not just simple statistics in order to do some sort of calculation on the adjacency matrix. Instead, if we want to ask something about what is the set of components in a graph, that you can't extract from the adjacency matrix by doing sums very easily. Instead, you have to use something like breadth first search or Dijkstra's algorithm. Does anybody know the trick for remembering how to spell Dijkstra's name? IJK, which is how we index things, right? I'm not sure if that's why we index things IJK, but it's a reasonable hypothesis. It's all Dijkstra's fault. So with breadth first search on an unweighted graph, you can compute the distance from one vertex to all others, and then you do that process for all vertices, and that allows you to get the pairwise distance matrix. It also allows you to extract the components, right? So if I'm in an undirected graph and I run BFS from some vertex x, I can reach all vertices that are connected through some path to it. I can then mark them as being visited, and then run BFS from the next unvisited vertex. And that will then collect its component, and so on. So I essentially run BFS a number of times equal to the number of components in the graph if it's undirected. And that can then give me the distance matrix. So that says for every pair of vertices, I now have some matrix here, I, j, where this value is the distance from I to j in terms of the number of edges between them. Infinite, minus infinity, plus or minus, whatever you want. Some special value that denotes the fact that they are not reachable. And this actually ends up being very critical for some calculations because, as I said just a moment ago, if a measure of network structure assumes that the graph is connected, and you run it on a graph that is not connected, that has two components, for instance, then some of those distances will end up appearing, and you have to know what those values are. So we'll see in a minute, maybe, probably not this lecture, maybe on Wednesday, two different definitions of what's called centrality, a certain kind of centrality score, in which if you have infinities in it, one score screws up and the other score does not. So there are ways of counting properly here so that you get the right kind of intuitive outcome. But generally speaking, if two things are not reachable, then we say that they're an infinite distance away. Okay. Okay. Yeah. Yeah.
In a random graph that node has 0 degree, the probability is nearly 0.
So it is possible to have a node with degree 0.
Yeah, but the probability is around 0. Does that?
So this is just a sketch. So if we want to take this literally and say that there is some density here, then that would say that there are some fraction of vertices that are singletons that have degree equal to 0. They have no partners. And each singleton node is a component by itself, right? It is reachable from itself via a path of length 0, but there are no other vertices that are reachable from it because it has no edges, and therefore it has no paths that are of length non-zero. Okay. If a network is fully connected, meaning that all pairs of vertices have a path to each other, then the density here at 0 will be 0. Yeah.
Does that give you the common neighbor matrix?
The common neighbor matrix?
Yeah.
What is a common neighbor? I have two vertices I and j. These in the middle are common neighbors. So each of these vertices is a neighbor of I and j, and so therefore this is a vertex that is a common neighbor of I and j. So these are not, these are vertices that are on path of length 2 for a pair I and j. That's what common neighbors are.
The common neighbor matrix for path 2 between I and j. Yeah.
So the question on the homework, I believe, asked you to count the number of common neighbors, right? So this is count the number of things that are one step away from I and one step away from j. Okay.
Like, what is like the neighbors? How do we consider for neighbors of I and I with respect to itself?
Common neighbors of I and I?
Yeah.
All of I's neighbors are common neighbors of I and I. Yeah, by definition. So if for a pair of vertices I and j, the common neighbors are those that are linked to both I and j. So the common neighbors of I and I are all the vertices that are linked to I and I, which are all the vertices linked to I. Okay. So why do we necessarily care about paths? Paths end up being a really crucial notion of imposing geometry on network structure. And we already know some interesting things just from the beginning about the sort of geometry of networks. One of them is that they typically have this property, which you've probably heard of before, called the small world property. So this term actually comes from a paper in the mid-20th century by Stanley Milgram. You may also know Milgram for his other unethical experiments. Well, I mean, this wasn't unethical. You may know Milgram for his unethical experiments, like making people think that they had tortured someone to death by electrical shocks. That's the same guy. He's also famous for discovering or recognizing or documenting the fact that large, real social networks tend to have this small world property. So essentially what he did was, here's my very poor picture of the U.S., Texas. OK, there we go. That's not too bad. So this is Boston. And he chose a random location in the United States, which in his case was like Nebraska. And he sent some letters to random people in a faraway place in the United States. This is in the mid-1950s and 60s. And in each letter was some instructions. He said, hello, I'm a professor at Harvard or wherever he was. I'm conducting an experiment about blah, blah, blah. Please help me do this. So the instruction said, there's a doctor. Here's the name of the doctor. This is a doctor, and it lives in Boston. So you had 3 pieces of information about a person. And the instruction said, I want you to send this package to the doctor, but you can't mail it directly. Instead, what I want you to do is pass this package to someone you know on a first-name basis, with whom you feel close, whom you think might be closer to the doctor. And that was basically it. Closer. More likely to know the doctor personally. So the rules of the game basically said you can only pass this packet along your friendship edges. You can't use the U.S. postal system to just mail it to somebody. And so, and then there was a ledger inside in which you would write your name. And so people did this. They would write their name and where they were and what they did, and then they would send it to a good friend of theirs who lives somewhere else. And what he found is that the packets tended to do this, which, as computer scientists, that looks kind of like binary search, right? It does a big step first, and then a step about half the size, and then half the size, and half the size, and so on. What?
Distance.
Yeah, the step, you can plot, because each person had to write down their mailing address, basically, or the town they lived in. You know sort of roughly where each person that received it was. So you can see geographically that at least the first few steps in each of these chains that was successful was typically just trying to get it physically close to Boston. But then once you got close to Boston itself, the search strategies changed. People instead would not send it to somebody who lived closer to Boston, but rather somebody who was more likely to know people in the medical industry. And so immediately you get this notion that people have this abstract representation of social space in their heads. They know that if they sent it to a doctor in Nebraska, that doctor was unlikely to know any doctors in Boston. If I get close to Boston and then I can switch dimensions, then it might be more likely to be able to use that dimension to reach this person. I know these 3 things about them, right? A doctor named this, and then they live in Boston. So the small world property is the observation that the length of these chains was about 5. The median number of steps in a successful chain was 5. So that's 6 degrees of separation. So 1, 2, 3, 4, 5, 6. Okay. So this is what the median length of the chain looked like. Now, only about 30% of the letters actually showed up in Boston. So what that also tells you is that people will throw them in the trash a lot. Right? They'd be like, I'm not going to do this today. I don't know anybody who can help. I'm in a bad mood, etc. But the fact that the median length was 5 implies that this social network that was being navigated, the length of these paths, was, okay, an integer. Is that integer big or small? That is a key question. So the argument as to why this is a small integer is the observation of how many people lived in the U.S. in 1960. Does anybody know that number? Yes. More than 5. Any other ideas?
Maybe about
go 10? 100 million. 100 million. Or that's 10 to the 8th?
H.
Yeah. Okay. So 10 to the 8th sounds like a big number. 5 sounds like a small number. So why is that surprising then? Here's the argument. Suppose I have a ring, and I make a network in which each node only connects to its neighbors. I'm not going to draw the rest of the nodes. And maybe to its next nearest neighbor. Okay? Etc. Okay? So if I choose a random location on this ring here, and I choose another random location on the ring, how long will it take for the message to get passed to that from I to J? However many nodes are either in this direction or this direction, whichever one is shorter. So if I have some notion of geometry, I know the addresses. I can say, for a given location, I can compute the remaining distance along local edges to get to J. Then at each step, I can, using a greedy, simple local algorithm, say, do I go this way or that way? Well, in this case, I go this way. So I would then walk around this circle. So if I choose any random pair of vertices, what's the expected length of the message chain in this case? And let's say we have n vertices.
N over 2, N over 4.
Order n.
It's order n. It ends up being, yes, n over 3 or n over 2, something like that. So the expected length, the expected distance from I to j, is big O of n. So if you have a world that has 100 million people in it, then the expected length of the chain is something around 100 million, on the order of millions of steps. But 5 is not that big. So how do we get from this big world to a small world? Shortcuts. So if I take some vertex and I rewire one of its local edges and I have it point across, like this. So now I have things that actually go a really long distance. Most of the edges only go distance 1 or distance 2, measured in terms of along the ring structure. But these edges here, these ones that cross, these chords that go through the middle, they traverse huge swaths of distance. They essentially have length of size order n. And so there was this very nice paper at the beginning of sort of the modern era of network science by Watts and Strogatz. Watts and Strogatz, 1998, I believe, in which they wrote down a very simple toy model for this kind of system. And it starts with the ring network, and it just says that there's some probability p that I rewire each edge that is not part of the ring itself. So every vertex has some degree that's bigger than 2. That allows me to make sure that the ring structure is always there. And then I have some other edges that go to my next nearest neighbors and so on. And so I'm going to rewire those next nearest neighbors with some probability p. So when p is 0, out here, you have the ring network. So this is, the distances are size order n. And out here at 1, I rewire everything. So that gives me essentially a random graph in the middle with this ring structure on the outside. So when I rewire, I just choose a random partner to attach to. So I keep my endpoint and I just choose a random partner. Okay. So here we have order n. It's known from random graph theory from many years ago that we have log n out here. When you rewire everything, you get something with an average distance of log n. So the question is, this is pretty big. This is pretty small, actually. So what happens in the middle? It must go down. So it goes down something like this. Oh, actually, no. I want to move it so I can draw something else. Okay, let's say it goes down like this. I haven't really told you what's in the middle here, so it's okay if I shift the curve a little bit. So this is the distance between things. They also looked at the clustering coefficient, which is just the triangle density. So notice that if I don't rewire everything, then there's lots of clustering, right? I have lots of common neighbors. If I choose 2 things that are distance 2 apart, they have a node in common as a neighbor. And this is a feature of social networks that's been well known for more than 100 years. If I choose 2 people who are friends, they have an edge between them, then they typically have a third person that they're both friends with. That creates a triangle. the triangles typically occur frequently inside social networks. So if I rewire the edges, then I lose those triangles. Out here, when I rewire everything, all the triangles are gone, essentially. And we'll actually derive that a little bit later, not today. So the question was, is it possible to have a network that has high clustering, lots of triangles, and short distances? We know that we can have short distances without triangles, and we can have triangles without short distances. That's the extreme, 0 and 1. So the Watson-Strogatz paper took this toy model, which is the first toy model we've seen in the class. It's very, very simple. It has one parameter. It's well-defined otherwise. And they just asked, what's the average distance between a pair of vertices, and what's the clustering coefficient, the triangle density, for various points along this axis? And this curve shows what happens with the path length. This curve, this curve shows what happens with the triangle density. So the implication is that somewhere in the middle here, you can have high clustering, high triangle count, and low distances. So it is possible to have this small world property that resembles real social networks. You can have short distance between all pairs of people and still have the sort of local structure in which you have lots of triangles and so on. That's what Watson-Strogatz showed. That explains to some degree how it is possible that you can have a distance of 5 in a network in which people typically only knew their local neighbors. All it relies on is that a few people in the chain know people that are further away. Yeah. P controls the probability of rewiring an edge.
Rewiring. Professor, what do you mean by rewiring?
I mean, I start off with a network that has only local connections. So each vertex connects to its nearest neighbor on either side, and then its next nearest neighbors. So that gives it a degree 4. So then, for each edge that is not a local connection, meaning that it goes either to my next nearest neighbor on either side, I have 2 of those. For each of those, I flip a coin with bias P. If it comes up heads with probability P, then I choose one of my next nearest neighbor edges, and I choose a uniformly random other node to attach it to. So this is what happens. I have a node right here. I choose this edge. I flip a coin. It comes up heads. And so I erase it. That. And now I choose a uniformly other random node, and I connect to that one. That's what rewiring means. Literally, like I have some wires, and I'm unplugging it there. I'm plugging it over there. Okay? And that happens with probability P. So when P is low, I'm only rewiring a tiny fraction of edges. But the critical insight here is that that's all you need in order to collapse the size of the world. You only need a few shortcuts in order to take something that looks like a big world and make it act like a small world. And you can preserve almost all the other local properties in the graph that you like, whether it's triangles or squares or whatever. It only takes a little bit of randomness in order to create these very short paths. What that means, of course, is that this short path will have many, many, many things that go across it, right? So this entire basin of vertices will all be using this highway in order to communicate, essentially, or connect to vertices on this side. So there's a non-uniform distribution of the paths across the edges now. Some paths are much more frequently, they occur much more frequently inside the shortest path between a pair of vertices. If you make things really random out here, then essentially all the paths are distributed equally across the network. But in this intermediate state, this disorganized state, you have these shortcuts, and those shortcuts are the ones that are very popular for connecting vertices. Okay. Okay. So this was a pretty important paper in part because it gave sort of a theoretical basis for how this thing could really happen. Right? People knew that this was an empirical observation. They saw this in the data. Milgram demonstrated in the data. But the question was, how could you have something as small as this and yet still have the kind of social structure that we know to exist with local connections? Okay. And they showed it with this very nice, simple toy model. As you're thinking about your projects, this is one strategy for exploring a property about networks or a question about networks is, can you cook up literally a one-parameter toy model in which, as you vary this parameter, you can explore some interesting state space. In this case, it was how the average distance varies at the same time as the triangle density varies. Okay. There's another implication that comes out of this, which is in many cases, we don't get to see the entire network. We have to sample the graph from the real world. Right? We have to go on Twitter and collect profiles and who they follow manually. Or using a program. But the point is that we don't get Twitter to give us all the data at once. We have to go and collect it by hand. Or perhaps we go into a high school and we ask people to name their friends. Any of these data generation procedures is a sampling procedure. There's some real-world graph, and there's this filter through which we interact with it. And we get to see a portion of it, but maybe not all of it. If you're in this intermediate regime here, where a small fraction of edges are driving the existence of a property, like the small world effect, for instance, if you happen to miss those in your sampling procedure, you will dramatically misestimate how big the world is. So for some network properties, sampling can have a huge impact. If it were the case that, so if this is 1 million vertices or 100 million vertices, and the edges that had been rewired are maybe 1,000 edges, that's a tiny fraction of all the edges in the entire network. And so if we have a small error rate in terms of how well we're able to perceive whether an edge exists in the real network or not, if we have that small error rate, we might miss these critical edges. And as a result, our estimate would be that the world is very big out here, when in fact, it could be much smaller out here. Yeah.
Is the way that you prove something is a small world network based on the percent of edges that are not nearest neighbor edges, or is it based on something else?
The answer is you don't. So there are people in the literature and outside of academia who want to do things like prove my network is small world. I don't know why they want to do this, except to be able to say that something. They may also want to prove that it's scale-free. And there might be some other properties, too. If I have some empirical data, maybe I want to know whether or not it has this property, either of these properties. And generally speaking, this is not the right question to ask, because this is a cartoon. This is a cartoon of the world. This is not the real world at all. If you were to try to tell somebody in the government that you were going to model some real system like this, they would laugh at you, because they're smart enough to know that there's no real system that looks like this. But the sort of conceptual idea of the world being small, of it not being the ring network, is that worth thinking about? Well, recall that we just argued that it just takes a small amount of randomness in order to convert a big world to a small world. So if your system has a little bit of randomness in it, it almost surely will be a small world. So really, it's more interesting if your network is not a small world network. Something like 99.9999999% of all graphs are small world networks. The only things that are not small world networks are lattices, essentially. And they're incredibly rare in real-world systems because real-world systems have a little bit of chaos in them, a little bit of disorganization, a little bit of randomness in them. It's possible to find big worlds if your graph is planar, for instance, because then it can be very expensive to have those long-range links. So imagine a road network. It's almost planar. So probably its diameter, its longest path, is going to be pretty long. It's going to be roughly the size of the entire. So those planar graphs are sort of the one case where you might expect to see something that is not a small world. But in general, everything's a small world. So what does it usually mean when we say something is a small world network? Well, there's a disagreement in the literature. There are two properties that get labeled with this. So it's 1 or 1 and 2. And this one is a diameter that grows like log n. This is a mathematical statement. This is a statement about a class of graphs that are generated by a mathematical function. This is a mathematical function. I've said I have a procedure that says I take n nodes and I arrange them this way, and then I rewire a certain fraction of them. That's a mathematical construction. And because I can measure the average path length as a function of how big I make the network, I can make a statement about this. The same thing is true for the Aaron random graph, which is if you rewire everything over here. That's a class of graphs. It's a mathematical construction. But if you can show that your mathematical model has this property, then some people would say, yes, that qualifies as small world. Other people say that it also has to have a triangle density that's high. And that's a vague word. We don't know what high means here. So in the Watson-Sturgatz model, they were using 1 and 2. They said, we want small paths, short paths, and we want lots of triangles. In the mathematical graph theory world, they typically ignore this one and just talk about path length. So in this class, and in all other interactions you have with people who want to talk about this term, you have to keep in mind that they could be meaning 1 or 1 and 2. So it's your job to figure out which one they're talking about. And they sometimes won't tell you. People who are mathematically inclined almost always talk about this one. People who have a background in sociology are interested in this one and this one. Yeah?
About 1, but sociologists care about 1 and 2.
I don't know. Culture. Yeah. I mean, academia is very tribal, and mathematicians, particularly the probabilists, have been studying random graphs as a family of things for many, many, many years, 50 years or more. And in their case, it's interesting when you can get this kind of behavior, or even log n. That's an ultra-small world, right? But the triangles for mathematicians are not interesting for whatever reason. I don't know, but they're not interested in that. And so they only care about this one. The sociologists, the triangle density ends up shaping so many local dynamics, right? Because it's how information gets propagated among groups and so on. So the triangles sort of shape the questions that they're interested in, whereas they don't shape the questions mathematicians are interested in. So depending on what tribe you're talking to, that will determine which of these two things they care about more. Okay, is there another question over here? Yeah.
Professor, but I think that if in the rigid lattice, there are triangles, and the rewire is not making more or less triangles.
Which model?
In that model. See,
This one.
Yes, there is a lot of triangles even before you rewiring it.
That's right. So out here, when p equals 0, the triangle density is also very, very high.
It's the highest.
The highest it can be. But when I start rewiring things, I choose an edge that essentially represents one side of a triangle, and I remove it, and I put it somewhere else.
Okay.
And so I reduce the number of triangles in the graph.
But I think that when you rewire it, it will create a new triangle somewhere else.
No, it will create a loop. So I erased it over there. So let's say I take this edge right here. So the triangle is, this is one side of the triangle, other side, other side.
Yes.
Right? Okay.
Yeah, that's a triangle.
So I take this edge, and I'm going to rewire it. That means I keep one end anchored, and I move the other end. So let's say that I keep this end here, and I'm going to move this end. And I choose some other vertex down here to rewire it to. So I've now broken that triangle. I've removed one triangle from the network, and I've instead created a loop that is of length this big. Okay? Okay. So the rewiring procedure reduces the number of triangles in the graph because it removes that third edge from each triangle.
So the small word means that it has a small distance. Meanwhile, high triangle density.
That's one definition of the small world property. You have the average path length or the diameter. It's vague about which one we really care about. Of the graph is order log n. And optionally, high triangle counts.
So the second is optional, the second.
It's optional depending on who you talk to, right? If you're talking to sociologists, they're going to care about triangles. If you're talking to a mathematician, they're not, typically. Okay. And both of those definitions go under the name small world property. In the mathematical community, small world networks are ones with short path lengths. In the sociological community, small world networks are ones with short path lengths and lots of triangles. Okay. Yeah?
The feature with high triangle density, then it becomes a random graph.
This is by construction a random graph. But it's possible to have short path lengths without it being a pure random graph. In fact, most real-world networks have short path lengths. Now, you can't determine whether or not they have log n because you can't generate various Facebooks with different numbers of people on them, generate different power grids with different numbers of power stations on them. You can't explore that spectrum. But what you can say is, I can compute the number and get 5. I can compare it to the number of nodes, which is 100 million, and say, it seems pretty small. It is possible to use random graph theory to compute an expected value. So imagine if I have the power grid network for the United States, and I compute the average path length between vertices on it. So that gives me a number. It's going to be a small number compared to the size of the graph. And then the question is, well, is that number about the same size as I would expect for a random graph? Well, now, using some tools we'll introduce probably next week, you can actually use random graph theory to make that calculation. So you can get a notion of how close to the expected value under a random graph is the observed value. And if it's within a factor of 2, then you can say it's small in practice. Okay. How are we doing? Not too bad. Questions about paths and small worlds. I didn't talk about scale-free graphs because we'll talk about it later in the class. Yeah.
Well, you're aware of this, but I think it was this last year, Facebook research came out with their new 3.5 degrees of separation, you know, according to their social network.
Yeah.
So I thought it was interesting. It's a little smaller than the 6 degrees, right? And maybe that's something about the mechanism by which people connect on Facebook versus how they connected in 1960.
Well, yes, it says a lot of things, and unpacking those things is an interesting exercise. So one thing, question it raises is the network that Facebook has a real network in terms of social interactions? And let me ask you, those of you in the room who interact with every single person that you are friends with on Facebook, please raise your hand. Yeah, okay. I think that question just answered itself. So computing sort of the average path length between a pair of people is a thing that you can do. It's a mathematical function. You can do it. If you have the graph, you can compute this thing. But the question is, what does this thing mean? And that's tricky, right? If you take the Facebook graph of who is friends with whom, then this is possible interactions, right? So it's possible that information could spread incredibly quickly across the Facebook graph because, on average, every pair of users is only 3 steps away from each other. But in practice, not everyone interacts with everyone, and so as a result, information will spread more slowly. So this number, 3.5, is essentially like a lower bound for the average path length of real interactions, of real information flow on that graph. Okay. There's a question in the homework, I believe, about the diameter of Facebook. It's on the extra credit, I think. And I ask you to think about this a little bit. The small world model is a good mental model for thinking about how changing one thing about the graph might change something else about the graph. That's a general strategy in network science, is to boil it down to a very simple observation. And then think about that one parameter toy model and how changing that parameter changes the things that you care about. It's a very powerful, intuitive tool. Okay. So we've talked about degrees, talked about paths. Now we want to talk about something called reciprocity. So in a directed network, I can have edge that goes from I to j. And if I have an edge that points back from j to I say that this edge is reciprocated. If we pass out a survey in this room and I ask you to name your friends, if I name you, then you name me, right? So you reciprocate my notion of friendship. It's not required, as I argued last time about it doesn't happen all the time. In fact, the empirical rate among high school students for reciprocating acknowledgments of friendship is about 30%. What? Well, it's public domain and stuff. So, but that statistic is funny because it confirms something we believe about high school students, or maybe something we experienced as high school students. But in fact, it's not that simple. Because the way that these networks are generated is I hand you a survey and I say, name 5 of your friends who are female and 5 who are male. And that's it. So you only get to list 5. What if you have 15? You have to choose which 10 you're going to leave off. And one of those 5 that you name might make a different decision about who to leave off. And they might not name you as a result. So they may still think of you as a friend, but the sampling mechanism that I use to get the data makes the appearance that the edge is not reciprocated. That's one mechanism by which you could get a low reciprocity in a network, even if there is actual high reciprocity in reality. Another way is that people don't remember who their friends are, which is also common, right? If I asked you to name everyone you're friends with on Facebook, go, you might be able to name 10, maybe 15, maybe 20, or 30, or 40 even, right? You think about, okay, who did I know in high school, in middle school, in college? Yeah, they're all friends on Facebook, and grad school, right? You might be able to list some fraction of them, but you wouldn't be able to list all of them, right? Because that's what Facebook is for. Its job is to remember those things and not you. So the mechanism by which you sample the graph can have an influence on what graph you see. Reciprocity is one way that you can measure something about a directed network. So the way you calculate reciprocity is very simple. It's R, which is for the entire network. It's an average over edges. And in adjacency matrix notation, it's very simple. It's Aij times Abi. Recall that if Aij is 1, I have an edge that goes from I to j. And if Aji is 1, then there's an edge that points from j to I. So if both of these edges appear in the graph, this product will be 1. So the sum over all pairs of this product gives me the number of reciprocated pairs of edges. And then I divide by the number of edges total. That gives me the fraction of all edges that are reciprocated. So this is a trick, right? Because I'm working with an unweighted adjacency matrix, I can use this simple product in order to select out the pairs of things that I care about. You can do this with other calculations too, we'll see in a minute. But this gives you the reciprocity, R. This is what we call a network level measure. In much the same way that the average degree is a network level measure. It tells you something about sort of an average vertex, in this case an average edge. It's averaged over the entire graph. You can also compute a vertex level notion of reciprocity. So a vertex level measure, like the degree of I. This would be the reciprocity of some vertex I. So we want something that looks like this equation, but we want it to be about the ith vertex. So what's the largest number of reciprocated edges that a vertex I could have? So we want to divide by its degree, okay? And then we're going to sum over some stuff. What are we going to sum over? Its neighbors, okay? So instead of summing over all pairs, we just sum over things that are not I, so j. And we do the same thing. Aij, Aji. That's terrible. I, J, J, I. 1 to n. Okay. If anybody's having a hard time reading my writing on this awful technology, please let me know and I'll try to write bigger. So this is saying I'm going to sum over all the things that are j, but I is fixed. I've chosen what I it is. So that's saying that I have some vertex here, and I look at all of its outgoing edges, and I ask how many of them are reciprocated. That's just sum over all the possible partners that I could have. This number here, this ki, is actually not exactly right, because we're in a directed graph. So in a directed graph, you actually have two notions of a degree. You have in degree and out degree. So ki in and k hopefully this joke will never get old in this class. It probably will. I, out. Okay. So the in degree is the number of things that point at I, and the out degree is the number of things that I points to. So the reciprocity for I should be this thing, which counts the number of pairs that include I, divided by what? Should it be k in or k out?
Edges should be from both sides.
So the claim is that it doesn't matter which one I put there. So if I put k in here, that should give me the same as if I put k out here.
Only if it's undirected. Right.
I think, so explain what you mean a little bit more. Why do you think it shouldn't matter?
Because we are taking dot product of ij and ji. So if one of them is 0, then it is 0. And if both are same, then in degree, it will be counted in degree as well and out degree as well.
So you're talking about this sum here. Right? So this is going to count some number, and it's going to be the same regardless of whether I think about things pointing in or out, because one of them is things pointing in and one of them is things pointing out. That's true. This term doesn't depend on whether we're thinking about things coming in or coming out. But this term does. So my reciprocity, how many of my friendships are reciprocated? What if I am a very popular person? I am the Justin Bieber of this network. That joke only works because you all are not young. Who's the most popular person if you're like 16 now? Does anybody know? Yeah, see. We're all old, just like me. Okay, so if you're the Justin Bieber of this network, then you have a huge in degree, but you might only have one edge going out. I don't know this to be true. So if that edge is reciprocated, then the number of your friendships, the people that you would name as friends who reciprocate that statement, is 100%. So it does matter with k out or k in here. And in some sense, it depends on what we're calculating. We're calculating how many of my friendships are reciprocated or how many of everyone else's friendships with me are reciprocated. And if you care about how many of my friendships are reciprocated, then you do k in on the bottom. If you care about how many of other people's friendships are reciprocated with me, how many of other people's friendships I reciprocate, then it's. So it's all counting, but what you count depends on what you care about. So if you care about my friendships being reciprocated, then it's not this. Okay? So when you're doing network analysis, when you think about your projects, for instance, it really matters. You have to think through logically, what does it mean when I calculate this thing? Is it representing the concept that I care about, the quantity I care about? Because this is just, a graph is just data. Right? You can compute anything you want about it. But whether or not those computations mean anything depends on what question you're trying to answer. Okay. Okay. Questions about reciprocity? Yeah.
K in plus K out.
Is K,
In plus out.
Is this true? Well, Ki, an undirected notion of degree, is not defined on a directed network. And so in some sense, this doesn't make any sense. Because in a directed network, edges either point in or they point out. If I were to ignore the directionality of an edge, to take a network that is not symmetric across a diagonal and to make it symmetric by ignoring the directionality of all edges, then you could ask that question. Does the degree on the directed version of the graph equal the degree on a graph that I make undirected? And the answer to that question depends on another question, which is whether you're talking about a multigraph or not. Recall that a multigraph is one where I can have multiple connections between I and j. See where I'm going with this? Do you see why this is an issue? So if I have 3 edges that point out between I and j, and I want to convert this graph into an undirected graph. I now have 3 undirected edges that go between I and j. If that's okay, if the world I'm working in is a multigraph world, then fine. I have 3 undirected edges from between I and j. And if there's an edge that points back here, now I have 4 undirected edges between I and j, because I ignore the directionality of these edges. But if you demand that you have a simple graph, which means that multi-edges are not allowed, then I collapse all 4 of these edges into one. So in a multi-graph context, this would be true. I take everything that goes in, everything that goes out, and I ignore the directionality. I allow multiple connections, and so therefore my undirected multi-graph degree is just the sum of these 2 things. But if I force myself back into a simple graph, then anything that's reciprocated is an overcounting. Because an edge that points from I to j is reciprocated by an edge that points from j to I. So that means there are 2 undirected edges. But when I simplify things, I lose one. So that means that the sum of my in and out degree is not equal to my undirected degree. So this is another wrinkle. You have to specify whether you're working with a multigraph or a simple graph in order to be able to say something like this is true. Okay. Generally speaking, we like simple graphs. Most calculations in the class, simple graphs. So multiple connections not allowed. Undirected edges, unweighted edges. The adjacency matrix is binary, and it's symmetric across a diagonal. That is 80 to 85% of the stuff that we'll do in this class. But in real data, you will encounter graphs that are not that way. And so it's really important that you recognize when the simple graph calculations break down. And this is one where if okay. So we talked a little bit about triangles already. This is another thing people like to use to describe a network. It's called the clustering coefficient. And it's really just the triangle density. And the way we compute this, the thing we care about is this. So I have some I have some j, here is some other k. This edge here, these 2 edges here, represent a path of length 2. I can count paths of length 2 in the graph. The question is, how many of these paths of length 2 are actually closed triangles? So this goes by various names, path of length 2. It also goes by a wedge. So I'll write the names that people will use to describe this. Path of length 2, wedge, open triangle, which is a terrible term. And there may be some others. This is a triangle. As we already talked about, social networks are believed to have an overrepresentation of triangles relative to other kinds of graphs. It turns out that real life is more subtle than that. There are lots of non-social networks who have lots of triangles. And you can induce triangles in graphs by doing certain operations with them. But the point is that we want to know something about how many of these things are those things. So it should be clear that necessarily this is a larger set of things than this, because I don't care about what's happening here. I just count the number of paths of length 2, and I ask how many of them are involved in a path of length 3, such that the starting point and the ending point are the same. A path that goes I, k, j, and then back to I. Okay. So I can compute this. This is the clustering coefficient C, which is the number of triangles times 3 divided by number of, oh, I forgot one. Connected triple. triple. Number of connected triples. So why is there a factor of 3 on top? That factor appears because it's saying we have to overcount these things. Ah, exactly, yes. So I have a wedge here, I have a wedge here, and a wedge here. So each triangle that appears in the network actually has 3 wedges, which means that it's overrepresented down here if I counted the wedges. So I have to multiply by 3 in order to get this thing to be the proper size. Okay. You can compute this using an adjacency matrix really simply, which is the sum over triples ijk of a ij times a jk times a ki. That gives you a triangle, right? If each of these is a 1, then I have 3 edges that make a triangle. And I just sum those over all trios. And I divide by the sum ijk of a ij a j k. Yeah. So this counts triangles, this counts open wedges. Why isn't there a factor of 3 in this version?
It already comes in the summation part.
When you do the summation on the top, it'll...
Right. If I have some triangle, ijk, then there are 3 times I'll see it. I'll see it for ijk, jki, well, and the other one. And so this is already doing the overcounting. So this is a nice, simple way that you can count the clustering coefficient using an adjacency matrix. If you can store your graph as an adjacency matrix, then this is really simple to do. Most graphs that are big, you won't be able to store as a matrix. You have to store them as an adjacency list, in which case it becomes more slower. Okay. So let's illustrate how to compute the clustering coefficient with an example graph. Okay. Okay, what's the clustering coefficient here? 0, good, because there's no triangles. Okay, let's make some triangles. Taking them all? Yeah. Okay.
Yes.
Now what's the clustering coefficient? 1/2.
No, wait, no, actually it's just 1. I mean, 0, wait, no, 1.
No.
It's 1.
Yeah, see, it's a little bit tricky, right? It's actually not 1, by the way.
I was like,
So when I did this by hand,
Swan.
what I got was, so the clique has 20 triangles and 60 wedges.
But you have to multiply through.
And there are some wedges over here, too.
Yeah.
And they're not closed. So it's definitely not 1.
Okay.
When you go through and count these things by hand carefully, I believe what you get is this is not n. C equals 60 over 73, which is 0.82. So the intuitive idea that it's high is correct, right? Because a clique has a ton of triangles in it. It has the maximum number of triangles. If we ignore this part of the graph, that clustering coefficient would be 1. It has every path of length 2 has an edge across the end to make a triangle. But there are these paths of length 2. And so all of those end up reducing the clustering coefficient. But there are not that many of them compared to all the paths of length 2 over here, right? There are 6 vertices here, so that means that there are 6 choose 3 paths of length 2. I also forgot that one and that one. So that's why this coefficient ends up being pretty close to 1, is because there's a ton of things over here that end up adding to the clustering coefficient, whereas over here there's only a little bit of stuff that's missing. Okay. So this definition of clustering coefficient is a network level property because we're counting things without thinking about individual vertices. You can define a local level clustering coefficient as well, in which I ask something about how many of the how many of the wedges that vertex I participates in are closed. So number of pairs of neighbors of I divided by O that are connected. And this is number of pairs of neighbors of I. So the picture that you should have in your head is, here's vertex I, and I have some pair of neighbors J, K. And the question is, are they connected? Not easy to do dashes. Oh, dash, 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 dash. Okay. So I could have many neighbors, and it's for each pair of them I ask whether they are themselves connected. So this bottom term, I can actually compute that analytically. If I know my degree, I can already calculate how many pairs of neighbors I have, which is what? Yeah. So this is just ki choose 2. But the top line is non-trivial. Right? I have to say, for each of those pairs of my friends, do they know each other? Because that tells me of the wedges that I am the middle of. Right? So in a wedge, I have this shape. Well, I'm going to put myself here. And I ask whether or not a pair of my neighbors are connected. But every one of the wedges in the local clustering coefficient, I'm in the middle of. Okay. If you wanted to average this thing over all the vertices, you would say, 1 over n, the sum of ci. So you can compute an average local clustering coefficient. And here's a question. Is this equal to that?
Maybe.
So you're thinking no. You have to do something funny in order to get it to be equal.
Number of connected.
Right? They kind of seem like they should be the same, right? Because they're really counting the same things. In one case, I'm just counting all the triangles over the entire graph. In the other case, I count the triangles attached to each vertex first. Right? So there should be some connection between these two numbers. If I average the local clustering coefficient versus I just compute this thing globally. So homework. Optional homework. Exercise. Convince yourself that these two things are not the same. They are not. Except under very special circumstances, like a clique. And then, so first convince yourself that they are not the same, and then explain why. What they're counting is different. Because it looks like they're counting the exact same things, right? They're not. And this is a subtle point about network science, is that the average of a local measure is very rarely equal to the global measure. Because there's something funny about counting between these two things. Okay. It may be possible to figure out a way of making them equal to each other. And that is part of understanding why they're counting different things. Okay. Questions about clustering coefficients, reciprocity, path lengths, small worlds, degree distributions. This is really the bread and butter. This is really the flour and eggs of network science. These are the basic ingredients. Flour and eggs. I guess if you're Western, that's how you cook. But this This is the fish stock. And because when we're thinking about describing a graph, we very rarely can picture it in a way that's useful because there's too many things to visualize. And as a result, we have to describe it using features. And those features need to capture things that are useful and intuitive. And the things that we've talked about today, these are the basics. These are the basic notions of how you describe the structure of a graph. You count how many triangles are in it. You look at how many edges are attached to the vertices. You look at the variability of how many edges are attached to vertices. That's the degree distribution. You look at how big the components are. How many components are there? Those are all things you can use to describe the structure of a network. There are, of course, an infinite number of these measures. Any function that takes as input a graph and maps that space of all graphs onto a one-dimensional space, either positive integers or the real numbers or whatever, that's a graph measure. That's a network measure. So there are an infinite number of such functions that take as input some graph and give you as output some number. But most of these things are not useful functions. Right? You want these functions to tell you something intuitively about the shape of this graph. And so these, the ones we've talked about, these are what people start with. And I guess I'll finish on Wednesday with this section. We'll talk a little bit about how we see these things across different kinds of graphs. So there's a very nice review article by Mark Newman from 2003, 13 years old now, in which there's a table in it. And I reproduced the table in the lecture notes on page 19. And it has, how many networks are in this thing? Like 25 networks, which in 2003, that was a lot of data. 25 networks, at the beginning of network science, it took a lot of effort to get those things. And in this table, he computes things like the average path length and the clustering coefficient and some summary statistics about the degree distribution, et cetera. And you can, I have 2 minutes. I have 3 minutes. I will show you. Okay, let's see if I can do this. He's going to walk in the door in about a minute. Local PC. It's worth looking at how these tables and figures look. That's why I want to pull this up for you. So, okay. Okay. There's a handy table on page 18 with a whole bunch of ways that you can compute these summary statistics. This is the table from Mark Newman's paper in 2003, which shows you he had a bunch of social networks, information networks like the World Wide Web stuff, some technological networks like power grids and so on, and some biological networks. And he computed a bunch of summary statistics about each of them. And the question that I wanted to get into was, well, is there a pattern in terms of how these statistics we compute correlate with the domain that these things came from, or the size of the graph? So let's see if I can make this bigger. Here's what we find. So these are box plots showing network size as a function of category. So he only had 4 categories: social, information, technological, biological. And what you see pretty clearly already is that social and information networks are pretty big, and everything else is pretty small. Right? The World Wide Web is billions of vertices, billions of web pages. Facebook is a billion people, whereas the power grid for the United States is maybe 1 million power stations, but that's about it. If we look at the average degree, everything's pretty small. These are sparse graphs. And then over here, this is the average geodesic distance divided by log n. So log n comes from that expectation from a random graph, so we're just normalizing with respect to that. And we find that all of these things also are pretty close to what a random graph would say. These are all fairly disordered systems. Okay? We can plot these things against each other as well, and that's what these figures at the very end show us. This is average degree as a function of how big the graph is, and there's not much pattern there. It's just this scatter. You see that biological networks are small, all down here. Social networks are much bigger. Information networks much bigger. Maybe there's a positive trend. The bigger your graph is, the higher the average degree. That's kind of an interesting observation. And then over here, this is the mean geodesic path length as a function of the size. So if it's the case that things are growing like log n, we would expect to see a linear relationship here, which is about, if you squint, what you see. I'm working on new versions of these figures that use about 2,000 graphs. There's this thing called the Index of Complex Networks that my group is building. It's an index of all real-world network data. There's a link off the class website. You're welcome to use this index to find interesting data sets that you'd like to explore for your class project. But the point is that we can learn something about sort of the space of all graphs by looking at all real-world graphs and try to get some insights about what are the general patterns among these simple summary statistics across both size of networks and where they came from. All right, see you on Wednesday. The sign-in sheet. Office hours are today. Upstairs.